You can see my screen now.
Yeah, we can see the screen.
Yeah, okay. This is Prabhakaran. I'm the current chair of CIBSE Young Engineers Network. So I would like to welcome you all for this technical event. So the event is about degassing systems in closed loop HVAC network. So before we get into the event, I would like to share few informations, the session notes, which need to be followed through the session. So most of you might have already familiar about with CIBSE. So for those who are new, I just want to give a small introduction about CIBSE. So CIBSE is basically a non-profit organization which is related to building services industry. The headquarters is located in UK, and we have several chapters around the world. Here we have CIBSE Main Committee, CIBSE Young Engineers Network, CIBSE Abu Dhabi chapter, SOFI, and so many subgroups we have with CIBSE. So the ultimate aim of CIBSE is to promote the welfare of its members and improve the understanding of building service engineering across the region. And we try to organize one event per month from each subgroup. So in order to provide a platform for the people working in the industry, a platform for networking and knowledge sharing opportunities. So the event agenda, I'll just walk you through the upcoming events which we have planned to organize in the coming months until December, and then followed by a small introduction about the speaker and the session notes which need to be followed throughout the session, and then the presenter will take it further. So the events which we are planning in the coming months are submersible wastewater pump with integrated intelligence, seminar on IES VE for lead and estedema modeling, importance of indoor air quality. So these are the events which we are planning to organize in the coming months until December from CIBSE YEN. To give a small introduction about the speaker, so Mohammed Farid, he is the technical manager, is working with Reflex. So he's specialized in mechanical engineering. He's been working with Reflex for quite a few years. He have worked in many of the medium and large projects in the industry. So he's specialized in the equipment selection, right equipment selection as per the project requirement. So he's also closely working with their R&D department, which is located in Germany. Few notes to follow. If you have any question and answer, please write it in the question and answer panel. So all the questions will be answered during the question and answer sessions. Please turn off your mic and camera so that the event can be conducted smoothly. So from here, the presenter will take it further.
Good afternoon, everyone.
Good afternoon.
Can you able to see my screen?
Yes, we can.
Thank you, Prabhakar. Thank you for this introduction. So today we will be discussing about the deaeration and degassing of HVAC system. So the agenda will be this short overview about our company, and next the basic principles behind the air separation and what are the importance we have, and the types of deaeration available in the types of technology available here, and how the air separation is happening, and then we will discuss more on the atmospheric degassing and the vacuum degassing systems. So Reflex is basically a German-based company, and we are providing the leading solutions for the air separation, pressure maintenance for the past 6 decades. So the basic principle for the air separation is derived from the law called Henry's law. So what the law says is the gas solubility is proportional to the pressure in the liquid. It means the more the pressure you have in the system, the more amount of gas is dissolved in this liquid. So we use this concept to expose the system water in a vacuum spray tube to reduce the gas content, which in the later on slide we will discuss more on the vacuum degassing principle. So if we take any as a normally water will have dissolved gases by default. At least you will have 11 milligram of oxygen and 18 milligram of nitrogen per liter of water if you take any on average, but depending upon the geographical location, the dissolved gases concentration can change. So this slide, what we see here is the impact of the solubility of gas depending upon the temperature. For example, if we take a liquid of 90-degree temperature, let's say water, it will have at least 3 liter of air for every 1000 liter of water. As the temperature reduces, you can see the solubility increases. So when the colder the water, more is the dissolved gases in the system. So when you apply it on our chilled water circulation system, so this is your circulation system where we do a continuous water makeup to maintain the system pressure. So as the water makeup increases, it will have the impact of oxidation because air is having oxygen and nitrogen. So the oxygen is getting reacted with a metal pipe and it is getting oxidized. Whereas the nitrogen, it stays as bubble or it stays as a layer within the pipe, which is creating friction and it can create heat transfer loss. So this is the negativity of improper air deaeration. So what is the effect is, so when you have a clean with the proper degassing system in your loop, you will have no damages for the pipe and there will be no deposit in the pipe in the system, and the water is circulating freely without any hydraulic imbalancing, and the heat exchange is optimized. So we have a proper heat transfer. In case if the pipe is corroded due to the air in the system, your pipe diameter is shrinking, which can really lead to the low water flow. It means we will not get sufficient flow in the last FCU, which means the heat transfer, the cooling cannot be achieved. And of course, you'll have a hydraulic imbalancing, and then you will have a lot of air problems like noise or gargling sound in your system. So the practical example which I'm displaying, you can see in the screen. For example, if you see the picture number 2, here you can see a strainer which is been crushed out because when the pump is sucking water, due to a large amount of air is entering inside, it is damaging the strainer and it is getting stuck in the pump casing. And for example, picture number 3 is related to the impeller is getting damaged due to the cavitation effect. And if you see picture number 6, is related to the mechanical seal. So when you have more amount of air entering in your pump, it can damage your mechanical seal as well. So there are several examples which we come across during the commissioning stage of the project when you don't have proper air separation. So next I'll move on to the types of deaeration. So there are 3 classifications of 3 types, I would say. One is called venting. Venting means we just remove the free air available in the system, which is mostly you can see on the top side of the circuit, higher level of the circuit where we have a free air. So when we have an air vent, we can easily remove the free air. But as you go a little bit lower, your water pressure is increasing, by which the air is will be in the form of bubbles circulating. So when we use an air separator, we can able to remove the bubbles as well as the free air. And as you go down the system on the vertical position, you will have a higher pressure in the lowest point. So here in this situation, the air is getting dissolved in the water. So it will be very difficult for an air separator or a venting equipment to remove the dissolved gases. Here, the degassing, the vacuum, the degassing principle comes into effect, which we call atmospheric degassing or vacuum degassing. So what is the efficiency comparison of this product? We have an air separator, we have atmospheric degassing, we have vacuum degassing. What is the difference between these three equipments, although it does remove the air from the system. So when you see this graph, you can see in the x-axis, it shows what is the static pressure of the system, where the equipment is being installed. And the y-axis says how much is the gas content at the outlet of this equipment, for example, air separator or atmospheric degasser or vacuum deaerator. So the curve of an air separator you can see on the diagonal side. So let's assume the air separator, which is having 4 bar inlet pressure. I mean, when you have a static pressure of 4 bar, you will have the gas content coming up with certain amount of gas content. When it is going out, it will remove some certain amount of gas content, but the efficiency will drop depending upon the inlet pressure, which I will explain in the coming slide. So, sorry. So let's assume that we may have 4 bar inlet pressure. The water is coming with 4 bar inlet pressure, and it's going with maybe around 3.8 or 3.9 bar due to the pressure drop. But there is no significant pressure drop over here, so by which the air removal process is getting reduced. So lower the pressure, better the air separation for the air separator. So how it works as an air separator? So we have, if you can see the cut section of an air separator, so where we have internally a copper wire mesh, which is in a form of honeycomb structure. So when the water is passing through this air separator, the velocity is getting reduced, means the pressure is slightly reducing, because here you have a bigger, smaller pipe, but here you have bigger cross-section area, by which the pressure is slightly dropped, and this wire mesh will obstruct the flow and creates a turbulence effect, by which the bubbles will try to go up, and as the volume of air bubbles becoming free air, the float is pushed down and the air is getting released. So this is for air separator is highly effective whenever you have a low pressure application, means whenever the air separator is installed in a lower pressure area. So you can see the typical installation. This is a boiler circuit, but in fact, when you go for chill water system, we need to install this air separator on the basically before the pump suction in ideal situation, so that we remove the air from the system before it reaches the pump and the chillers. So the next is the atmospheric degassing. So atmospheric degassing is basically an equipment which does the pressure maintenance of the system, water makeup, plus it does an additional function of air separation. So how it works? So you can see an expansion vessel here, but in this expansion vessel, there is no pre-charge gas in the system. So it's open to atmosphere, but we have a water which is inside the bladder, and we have two pipe connections. One we call expansion line, other one is called filling line. So these two pipes are connected to the main header of our system. So when the system pressure or the temperature increases, so the water is expanding in a molecular wise. So as the pressure increases, there is a motorized valve. The spill valve will open to allow the water to expand in the expansion vessel. So now what happens? We are exposing the system pressure, which is, let's say, which is at 5 bar pressure, and it is getting exposed in an expansion vessel, which is kept at atmospheric pressure, because there is a small vent opening by which the atmospheric air can enter here. So there is a huge shift of liquid pressure is happening. Like for example, from 4 bar, the pressure is going to 1 bar. So by which the Henry's law comes into picture. So solubility of gas is proportional to the pressure in the liquid. So when you have a low pressure, the gases in the water comes out, and through the air vent, which is on the top of the tank, the air is getting released. So this we call it atmospheric degassing. So once the complete expansion is taking place, this tank can able to accommodate 90% of the expansion in the system. And for example, 90% of the tank volume can be utilized for the expansion purpose. So in the maybe on the next session, I can explain more about this dynamic atmospheric degassing system. So when the pressure is getting normalized in your getting stabilized, the water will go back automatically through the pump to the system. So this is the, excuse me. Okay. So where we are installing this equipment as a arrangement wise. So if you see the chill water circuit here, boiler or a chiller circuit, we install this equipment in the return line. We take 2 tappings and we have a pump scale with multiples of expansion vessel in case of bigger projects, bigger system volume, or we can just go with a single expansion vessel, which does the atmospheric degassing. The main topic for today is the vacuum degassing. So the vacuum degassing is basically the principle is divided into 4 steps. The first step is called creating vacuum in this tube. Next is doing the degassing function. The third, we call it exhausting, which is the most important step in the vacuum degassing principle. And it goes to the standby mode off time after completing this circulation, after completing the cycle. And then it does the continuous cycle to be repeated again, 4 steps. So how it operates? So this is a vacuum spray tube, and on to the inlet we have 2 pipe connection. One we call system water and the makeup water. This tube water is connected to a 3-way makeup 3-way valve, and the water is passing through the tube through a nozzle. Inside the tube we fix a nozzle to spray the water inside. At the bottom we have a pump which is sucking the water from this vacuum tube. So the first step we call it vacuum. So what we do is we run the pump so that we take the more water out of the system, but we give less water through the nozzle, by which we create vacuum. So as vacuum means basically the negative pressure. So we expose the system pressure water, which is let's say at 4 bar with gas rich. When it is exposed in the negative pressure, which is negative pressure means very, very low pressure. So the boiling temperature of the liquid is getting reduced. So by which the gases which is in the water comes out automatically, and through the air vent the air is getting released. So the next step is called degassing. So we continuously run the pump for certain seconds, and then we continuously spray the water through the tube. Exhaust. So exhausting is we stop the pump, but we continue spraying the water. So here the water is getting relaxed in a vacuum condition, so which the more amount of gas is getting released, and as the water volume increases, the air is getting compressed and then it is getting released through the automatic air vent on the vacuum tube. And once the cycle is completed, it goes for the rest time, which is for 3 to 5 seconds. And again, the cycle starts. It's basically a side stream function by which we remove more amount of gases from the system. In fact, the free air, bubbles, and the dissolved gases from the system. So where we are the ideal location for this vacuum deaerator, the system is on the return line, and most importantly, where you have a high pressure. For example, when you take an example of high-rise tower, we have an ETS room. From the ETS room, we push the water to the highest, to the last floor on the higher level. So we need to install this vacuum deaerator on the ETS room, where you have a high pressure. It means the more amount of gas is getting dissolved. So when we use this equipment, we can remove more amount of gas from the system. So this is the animation video how the vacuum degasser is working. So this cycle is basically 90 to 120 seconds, depending upon the system size of the project size, and based on the volume, we design this product. Irrespective of our manufacturer's different concept, the cycle is usually between 90 to 120 seconds. So we can do the degassing of our system water as well as the makeup water. So how this air is creating an impact on our energy efficiency. So what is the importance is when you have a high gas content of water, which will be having creating a less heat conductivity, less specific heat, and less surface temperature. In case if you have a low gas content of water which is circulating in the system, you will have your more heat transfer is happening, your specific heat capacity increases, as well as the heat dissipation is increasing a lot. So I just show you a small example of our floor heating system, how useful when you have a vacuum degassing in our circuit. So when you have a system with 55 milligram, which is high gas content, which is having a room temperature of 20 degree, and the middle temperature on the floor heating system is, let's say, 26.77 degrees Celsius, and it has a specific heat of 73.1 watt per square meter. In case if we have the vacuum degassing system in our floor heating system, we had an increase of 4.8% of heat output. So if you make it in the thermographic imaging, you can see here, this is a radiator. Okay, if you can see the red area, which is the more heating is happening through the radiator when you have a vacuum degassing. If you don't have vacuum degassing, you can see the heating area is very, very less. It means your heat transfer to the ambient or the room it takes more time. And if there's another one image you can see here, where you can see the heat dissipation is very, very less because of the air in the system. In case if you have a vacuum degassing system, you can see the heat transfer is increasing a lot. It means your work to the load to the pump, circulation pump, and the boiler or the chiller is reduced. It means you are saving more energy. So as a summary, so when we have the vacuum degassing system, we save a lot of energy because we remove the air from the system, and we reduce the chemical consumption because there is less corrosion. It means we have a less chemical consumption, and it reduces significantly the commissioning time, and it streamlines your flow, so there will be no hydraulic imbalancing can happen. And most importantly, it will increase the life of the asset of your system, which is your pump, chillers, and your radiators, FCOs, AHUs, and it will also reduce the hydraulic the shock, which is the back pressure created due to the different the back pressure created due to the air in the system. So these are the advantage when we go for a vacuum degassing principle, which can reduce it can reduce a lot of problems which we are coming across in the nowadays chill water system, because we always go for air separator, but unfortunately the air separator has a less limitation because it doesn't give me any output because the inlet pressure is more than 0.5 bar, which will not help the client to remove the air from the system. Of course, the vacuum degassing principle helps a lot, and it reduces the installation cost also, not only the energy saving operating side, even on the installation investment cost for the product, it is very less comparing the air separators and the other air separating equipments. So any questions?
Okay.
Any questions? Right.
For it, I can see one question on the meeting chat from Jason Fathers, which is mentioned on the previous slide. Would it not be preferable to move the air separator to before the pump to reduce the water pressure within the device? You will find it in the meeting chat.
Before the pump to reduce the water pressure. Yeah, but the idea of having the air separator before the pump is when you have air which is passing, circulating the system. So before the air is reaching the pump, we want to eliminate it, because when you have air in the pump, it can affect your pump casing, and as well as the cavitation effect will happen. It means your impeller will be getting damaged, which means your pumping efficiency will drop. So that's the idea behind to keep the air separator before the pump suction side. So did I answer your query, Jason? Hello? Yeah, there is another question from Azhar Ali, saying, is there any rule of thumb when to use venting, separator, and full degassing? So I would say that venting is necessary, because on the every high points we need to fix an air vent. When you fix an air vent, we need to fix an air vent with check valve, because when you see most of the air vent, it doesn't have any check valve. Means the air can infiltrate from the ambient to the through the air vent. To avoid that, we need to have a check valve along with the air vent. This can be installed in the higher level of the system, high points. But separators, again, like I said, it depends upon the inlet pressure of the system. I'll just describe on this. Yeah, if you see this graph, you can see the air separator curve is here. So when you have 4 bar inlet pressure at the inlet, at the outlet the gas is getting released, but there will be some amount of gas in the system, which is, in this case, you will have 65 milligram of gas per liter of water is always available, or it will be reduced. And even if you do thousands of cycles through the air separator, your output is fixed, 65 milligram. Your ideal function of an air separator, it means when you have 100% efficiency, at the outlet of an air separator, we need to have 15 milligram. In this situation, your air separator is working perfectly fine. Means I'm removing the free air and the bubbles from the system. When I'm removing these two components, I should have 15 milligram per liter of gas. But when you have 4 bar pressure, you can see this graph says you will have 65 milligram. So in this case, the air separator will not be efficient. We need to go for atmospheric degassing or dynamic vacuum degassing, which is independent to your static pressure. In case if you want to use an air separator, we can use it only on the heating system where you have a very low inlet pressure. Or unfortunately, in our region where you have a cooling system, our inlet pressure will be usually more than 1 bar or 2 bar, so the air separator becomes inefficient. And what was the other query here? The other query from Fuad is saying, what is the difference between you and Spyrex Satco? The Spyrex Satco is basically they work for the heating the hot water system where they use the air separators, which is mechanical one. We can do the air separator mechanical type, but we also do the vacuum degassing, which is far better than the air separator in terms of the working principle. And Mr. Jordan Great Pringle has mentioned the question from Floyd Castro saying that if I'm installing the air separator on the high pressure application, in the high pressure application, we suggest to use a vacuum degassing principle instead of a mechanical air separator. So because like I said in the previous graph, higher the pressure, inlet pressure to the air separator, lower the efficiency. So it's better to go with vacuum degassing principle. Any more questions, guys?
Hi, Farid. I think the question is regarding whether the product is applicable for to be installed before suction. I think they're asking about the suitability of our device for the pump high pressure application at the suction side.
Yeah, we can install the air separator. Nothing wrong in it. But when you have a high pressure means you have a more static pressure. So in this case, the air separator is becoming inefficient because there is no significant or no huge pressure difference between the inlet and the outlet of the air separator, so which will make the system inefficient. So in this case, vacuum degasser will be the best principle to deploy so that we remove more air from the system. Okay, Mr. Ford is saying how to separate metallic debris. So to remove the metallic debris or the debris or the sludge in the system, we need to use a dirt separator. The dirt separator is basically the, I would say the I'll just share you the screen. So now you can see on this screen this air separator. So when you make this air separator in the opposite, just make it 180-degree turn. So remove this air vent. So through this wire mesh, you can able to remove the dirt particles from the system. And with this dirt separation, we can go up 5 microns.
Mr. Farid, the screen, you cannot see the screen.
Can you see the screen now?
Yeah.
You can include the direct picture of the dirt separation. Is the screen visible now?
Yes, it is visible.
What was asking how to remove the dirt from the system. So what we can do is we can use the dirt separator. Again, this should be before the on the return line, before the all the equipments on the return line. So the water is passing through this copper wire mesh. This copper wire mesh will create the turbulence in this area by which the dirt particle settles down and the clean water is getting circulated in the system. So with this dirt separator, we can reduce the magnetic particles and the sludge, because when the water is continuously circulating in the system, the water can start erode the iron particles in your pipe. So what we can do is we can fix a magnetic rod to attract the iron particles, and plus we can also separate the sludge from system. We can do up to 5 micron efficiency, means better than the wide strainers, because wide strainers, depending upon the pipe sizes, the perforation is changing. Okay, so by which, for example, if you take DN65 strainer, it will have a perforation of at least 1.5 to 2 mm hole, which means 2000 microns. So when we go for a dirt separation principle, the efficiency is up to 5 microns. It means we have a very clean water. It means the more the dirt is getting removed from the system, the more the heat transfer is happening. Because when you have a dirt and the iron particle floating in the system, it can absorb your cooling or heating energy. It means which is inefficient for the chiller and pump operation. So dirt is an important factor. Dirt separation is an important factor in the closed loop system. Can't see. Target over content review. Any more questions?
Okay, it seems that there is no more questions, so we'll wrap up the session. So
Yep.
I'd like to thank everyone who were attended. I hope it would have been useful for everyone, and a special thanks to Mr. Farid for delivering this presentation. It was indeed a wonderful presentation. Thank you, everyone.
Thank you all. See you soon again in the different topics.
Yeah, sure. Thank you.
Yeah.
Thank you, everyone.